The first trigonometry unit deals primarily with what we would call trigonometric functions. And by functions, what I mean are not only the graphs of sine and cosine functions, but also trigonometric functions on the coordinate grid. X, Y, and R, sine theta, cos theta, tan theta, cosecant theta, secant theta, cotan theta, all of that stuff. What this second, and in the first unit as well, we deal with some equations. We learn how to solve linear trigonometric equations and quadratic trigonometric equations. This second unit deals primarily with what are called identities, although the first part of it is still going to be focused on trigonometric functions, because that's just where I've decided to split all of the trig down the middle into two equal parts. And then at the end of this unit, we're also going to be revisiting solving equations using what are called identities. And although we don't need to know this for today, I think as an introduction I should explain to you what an identity is. An identity is a statement that's always true. There's a little exception to that we don't need to get into today. When we officially learn about identities, I'll talk about that exception. But this top statement is an identity. I mean, it's meant as kind of a jokey meme that sine of gerene plus cos of gerene equals tangerine. And what I'm telling you is the sine of an angle divided by the cos of the same angle always gives you the tangent of that angle. And you could try that on your calculator, and it really doesn't matter whether you're in degrees or radians. I happen to be in degrees right now, so if I take, for example, sine of 85.2 degrees, and I divide by cosine of 85.2 degrees, I get some number. That's the ratio of sine of theta to cosine of theta. If I were to take tangent of 85.2 degrees, I get the exact same number. And that's a pretty easy one to figure out, given that sine is y over r and cosine is x over r. If you take y over r divided by x over r, you're going to end up with y over x, which is tangent. Okay. The bottom one, and again I presented it kind of in a meme-ish fashion, says that if this zebra is sine squared of x and this, I guess it's a donkey, is cos squared of x, when they mate, you get this guy. There's a name for this, but it's escaping me right now. What is it? Do you know? Oh, I thought I heard it. But cos squared of x plus sine squared of x is always 1. And that probably shouldn't be a big surprise to you either, because cos of x on the unit circle is the x coordinate, and sine of a rotation angle on the unit circle is the y coordinate, and x squared plus y squared equals 1. So that's what most of the unit is going to be dealing with. If you were to take a look at this whole bucket list of things we have to cover, you will notice a recurring theme throughout. Identities. Trigonometric expressions are going to crop up in identities. Identities. Most of this unit is dealing with identities. But the first 2 days of classes are going to be dealing with the first two things. We're going to be looking at the graph of tangent of theta. You know what y equals sine of theta looks like. Starts at the origin, goes up and down, and repeats every 2 pi. You know what y equals cosine of theta looks like. It starts up at 1 and goes down, down, up, up, and repeats every 2 pi. We're going to learn what tangent of theta looks like. We're also going to be solving trigonometric equations graphically, and more specifically, when we get back, we're going to be solving sinusoidal applications. Just so you know, that word sinusoidal means cosine functions or sine functions. There are some things in nature that follow those patterns. Forgetting about daylight savings time, if you record the time of the day that the sun rises every day throughout the year, you discover that at the first day of the year, the time is quite late because you're kind of in the middle of winter. And then as the days go by, the time starts getting earlier and earlier and earlier. And then on the longest day of the year, the time of sunrise is the earliest, and then the days start getting shorter. And if you follow my finger, what's happening is you're getting some kind of a curve. For people who live near the ocean or near bays where the ocean has tides that come in and out, the depth of the water in a harbor goes up and down regularly, and it does it regularly. It's periodic. It takes 12 hours to go back to where it was. These are all examples of sinusoidal applications. But let's get started with today's lesson, which is kind of an amalgam of two different ideas. No, I shouldn't say that. It's not an amalgam. It's just two different ideas. They're not necessarily connected. Okay? An amalgam is a mixture. This is not a mixture. We're going to be looking at the graph of y equals tan of x, or f of theta equals tan of theta, if you want to use theta instead. And we're going to be solving trigonometric equations graphically using our graphing calculator. So to begin with, we are asked to sketch y equals tan of x on the grid with the aid of a graphing calculator. The first thing I want you to note, though, before we actually get to the graphing calculator, is that, and you don't need to mark up your grid with all of this, but this is pi over 2 radians. And you should know by looking at the unit circle, without even going to your calculator, that when you get to pi over 2 radians, tangent, which is always y over x, is going to be y divided by what? X. What's x at pi over 2? What's the x-coordinate on the unit circle at pi over 2? Miles, do you know? So let me draw the picture. I'm talking here about the unit circle, and a rotation angle of pi over 2 radians takes us to this point. What is the x-coordinate there? 0. So what is tangent of pi over 2? Well, it's not defined because you're going to go y divided by 0. Okay. If we were to take a look at pi over 4, you should know that at pi over 4, which is right here, tangent is 1 because x and y are equal to each other. This is basically from the first unit. So one of the things that we will discover here is that at pi over 4, we should have a tangent value equal to 1. And if you were to go to negative pi over 4, well, that would take us to here. You should get a tangent of negative 1 because x and y are equal but opposite. So there's going to be some key points to this graph. But let's get to it and let's take a look at the graph on your calculator. Now, we happen to be in radians, and I do want you to actually put your calculator into radians. Make sure you do that. And what I want you to actually do is set up your window settings manually to match this. So I need to go from negative 2 pi to 2 pi to match this grid. And I literally just enter negative 2 pi and then hit enter. And as soon as I hit enter, my calculator is going to take negative 2 times pi, negative 6.28 something. And then I want to go to 2 pi. If you were to take a look at the graph that we have here, horizontally speaking, pi has been cut into 6 chunks, which means that each of those grid lines is pi over 6. So I'm going to change my scale to pi divided by 6. It's not absolutely crucial. My minimum on my graph is negative 2, and my maximum is 2. And if you want to follow the grid lines on my graph that I've given you, each square, it's not really a square, but you get my drift, each increment on the vertical axis is half. And now we can put in y equals tan of x and take a look at what it looks like. Once again, everybody, the x, when we write y equals tan of x, the x is not x on the unit circle. It's x on this graph, which is actually theta on the unit circle. So we go graph, and we get this repetitive picture, and it does repeat. And it looks like that. Now, before we draw anything or commit to anything, you can note that there are a bunch of x-intercepts. But the biggest thing is it's not like sine or cosine, is it? Where sine just wobbles up and down between 1 and negative 1, cosine wobbles up and down between 1 and negative 1. This thing, and we can suspect this is true, it goes up and down forever. If I were to, you don't need to change yours, but if I were to change my window setting to negative 4 to 4, just to look further up and down, I discover that it just keeps going. And the reason for that is, if you talk about approaching 90 degrees or pi over 2 radians, so there's a rotation angle. If I increase that rotation angle, and I recognize that a point on here will give y over x equals tangent of the rotation angle, as I get closer to 90 degrees, the x-coordinate gets closer and closer and closer to 0. The y-coordinate gets closer and closer and closer to some number. But what we end up with is a fraction where the bottom is shrinking very, very close to 0. So it's going to explode. The whole fraction will explode to infinity. And what we end up having here at pi over 2 is an asymptote. You have a line that the function will approach but get deflected away from it towards infinity or negative infinity on the opposite direction. If you look carefully at your graph, the graph does have an x-intercept at the origin, and it does have an x-intercept at pi. Let's talk about that for a second. Why is the x-intercept of this pi? Well, looking at this graph, if we have an x-intercept of pi, what that's saying is tangent of pi gives you 0, gives you a y-coordinate of 0. Well, why is tangent of pi 0? Well, if you look at the unit circle and just follow my arm and I go over to pi radians, which is here, that has a y-coordinate on the unit circle of 0. So tangent, which is y over x on the unit circle, is 0 over 1 on the unit circle, which is nothing. And every time that arm sweeps around and lands in either this position, which if you're watching this on video, you can't see what I'm doing, and this position, anytime it lands on this side or this side, tangent of the rotation angle is 0, so that will correspond to an x-intercept. Similarly, anytime it lands here or here, you will get an undefined value for tangent, which will mean you'll have an asymptote. And if you look at, this is really a good way of visualizing it, if you look at the angular distance between here and here, or here and here, it's pi radians. And if those are x-intercepts on this graph, the x-intercepts are separated by pi radians. And the angular distance is the wrong word, but the angular measure or difference between the positions where we have asymptotes is also pi. So the asymptotes, and now we can start drawing this, the asymptotes will also be repeating every pi having some difficulties here. Give me a second. So I'll improvise. The asymptotes will also be repeating every pi. So these red dots that I'm laying down on the x-axis are pi apart, and the blue asymptotes are pi apart as well. And you can see what happens is you get this curve. It's going to go through here gently sloping up and here gently sloping down, and that thing is going to repeat every time in between those pairs of asymptotes. So what we're going to end up with is this situation. Now, I will get to in just a second what it is you need to know here. because the story with this graph is about to end very shortly. Okay, it's not something that we really do a lot with. But that's what the function looks like. And what I would say to you is if you're ever at a loss as to what y equals tan of x looks like, and where the x-intercepts are and where the asymptotes are, you graph it on your graphing calculator. And incidentally, if you enter y equals tan x, whether you're in radians or degrees, and you go, I want to go back to the window setting that you currently have. I told you to go from -2 to 2 for y, correct? Okay, and there it is. If you enter y equals tan of x and you go zoom trig, it's going to, I believe, use the same x settings, but it's going to go from -4 to 4, I think. Zoom trig. So if you're ever at a loss as to what this graph looks like, then graph y equals tan of x, go zoom trig, and there it is. Does anybody have a graphing calculator that puts some kind of jaggedy lines in between the curves? If you do, all that is your calculator making an attempt to connect different pieces where it shouldn't connect them. But you can think of those jagged vertical lines as being asymptotes. They're not actually part of the graph. They're where the graph doesn't exist. So we have questions to answer here. What is the domain? Well, this is not any real number, because at pi over 2, the function doesn't exist. At negative pi over 2, the function doesn't exist. Now remember, I told you that this location of this asymptote, which is at pi over 2, if I go down here to asymptotes, I can write x equals pi over 2. Right? That's where the asymptote is. But that means, and this is tricky, if the vertical asymptote is at x equals pi over 2, then the domain is that x is not equal to pi over 2. The equation of the asymptote tells you where that dotted line is, but that dotted line is where x is not allowed to be on the function. So we say the domain is x is not equal to that. We said that all of these asymptotes are separated by pi radians. Right? If I look at this distance here, from 0 to pi, that distance, well, that's the distance between the asymptotes. And all that means is the equation of the asymptotes will be x equals pi over 2 plus multiples of pi, where n is an integer. That'll do it. That'll just keep adding pi consecutively, 1 pi, 2 pi, 3 pi, and also taking away 1 pi, 2 pi, 3 pi. And we can do the same thing for the domain. This is different now because the range is y is any real number. Tan of theta is any real number because it goes up and down forever. It's not maxing out or minning out, and for that reason, there's no amplitude. The word amplitude has no business in a discussion on y equals tangent of theta as a graph. I put it there just to impress on you that there is no amplitude. If I leave it out, students tend to think I forgot it maybe or something. The period, don't forget period is k, is not 2 pi. Look at this graph. How often does that shape repeat? Every pi. So the period of tangent is different. And this is the one thing, well, they're all important, but this is the one thing that typically is tested on an exam. That you understand the period of sine theta and cos theta are each 2 pi, but the period of tan theta is merely pi. And that's it. And then I think we have the intercepts. Well, the y-intercept is 0. Lots of ways you can write this. Y-intercept equals 0. You can be more specific and give the coordinates. There are multiple x-intercepts. There is an x-intercept at 0, but didn't we say that the x-intercepts repeat every pi as well? So we can just put for the x-intercepts multiples of pi. That will include 0 pi, that will include 1 pi, 2 pi, negative 1 pi, negative 2 pi, etc. And what I will tell you is this is where the curriculum kind of ends with tangent of x. You need to know all of the properties of the graph of y equals tangent of x. The question then becomes, as a teacher, or as Alberta Ed thinks, how do I test this? I mean, I suppose I could just ask you outright on an exam what the domain or something is. But sometimes they will ask a question like this. They will say the period of a particular sine function is the same as the period of a tangent function, and then ask you about the sine function. You're told you have this function. I want to rewrite it. F of theta, or y, equals 5 sine times r sine of r theta over 7 minus 9, and the period of this is the same as the period of this. G of theta equals tan theta. Well, okay, just a second here. The period of tan theta is pi. And what this is now, what this is turned into now, since the periods are the same, you know the period of this function is pi, this is turned into a trig unit A question. Because when we take a look at this function, in this function, b is equal to r over 7. And you know there's a relationship between b and the period, which is that the period equals 2 pi over b. So we ought to be able to figure out what r is equal to make that happen. Because the period is pi, b is r over 7. I would highly recommend here, after you've done that substitution, don't use anything other with complex fractions than the idea that you multiply the top and the bottom by any denominator you want to remove, which is going to be vitally important when we deal with identities in this unit. So I'm going to multiply the top and the bottom of this by 7. This is going to turn into, well, the pi's cancel, but I'll just leave them in for now. Pi equals 14 pi over r. When I cross multiply, I get r pi equals 14 pi. The pi's cancel, r is 14. And that's the answer to that question. Good little numerical response question. And again, the only thing that separates this from the previous unit is now you know what the period of tangent is. Any questions with that one? Okay, example number 3, A. Solve this equation algebraically and also state the general solution. So I'm just going to step out for a second. Is it? It's almost 10:02. I have to meet with somebody quickly in the office at 10:02. I'm hoping it'll take like 1 minute, okay? But it's something that I need to do. This is a unit, trig A unit question, all right? You have to solve this algebraically, it says, which means you have to factor this, and then you have to set each factor equal to 0, and then you have to solve each of those new linear trigonometric equations. Are you with me on that? Okay. And just worry about from 0 to 2 pi, and then we can tack on what we need to tack on for the general solution. Sorry about that. Just by a show of hands, how many of you have the solution right now? It probably, I mean, after going through a number of these questions, it probably shouldn't take you that long, particularly if you're adept at visualizing and using the unit circle. The factoring is just a fact of life here. You just have to be able to factor this. It's not a difficult one. You often see this 2, 1, 1 combination in trigonometry. It's going to be 1 and 1 here. I want negative cos x, so when I FOIL that out, I'll get negative 2 cos x plus cos x, and it all works out. So what happens here is you get 2 cos of x plus 1 equals 0, and cos of x minus 1 equals 0, which means cosine of x equals negative 1 over 2 when you rearrange it, and cosine of x equals 1. I would really say to you that at this point, if you have to rely on using your calculator to find a reference angle, you're going to start to get in a bit of deep trouble here in this unit. We want to think a little more abstractly. In terms of the unit circle, cosine of a rotation angle is equal to the x-coordinate on the unit circle. I'm doing a bit of extra review here from the previous unit. It's equal to x on the unit circle, not because there's an x in those equations, but because there's a cosine in those equations. So when you look at the unit circle, that's not bad. Where is cosine? I'm just going to put them all on 1. Where is cosine negative a half? Well, that would be here, because x is negative 1/2 there, and here. These are the locations. These are not rotation angles yet. They're just positions. And where is cosine equal to 1? Here. So how do we put this together in terms of solutions? For the solution from 0 to 2 pi, we would say theta. You know what? I really wish there was a universal rule in high school, in math period, that we don't use x to represent a rotation angle. Because then I don't have to say every time, you realize this x that I've just written is not x on the unit circle. Although it turns out to be in this case. That we look at that idea to find the rotation angle. But what is the rotation angle to get to this first location? I'm going to letter these as A, B, C. Well, that's 0 and 2 pi. Do we include 0? Yes. Do we include 2 pi? Yes, because of the square brackets. So x or theta equals 0, 2 pi. What about b? At b, that's 1, 2 pi over 3. What about c? That's 1, 2, 3, 4 pi over 3. And we're done. If you want a general solution, you could do one of the following two things. You could say x is equal to multiples of 2 pi, which will give us the 0, the 2 pi, the 4 pi, the negative 2 pi, the negative 4 pi, all that stuff. And you could say multiples of 2 pi over 3. And you could say multiples of 4 pi over 3. Again, for all of this, where n is an element of the integer number set. But, and you just always have to be on the lookout for this, and I'm still back in time in Unit A. We haven't seen the connection to Unit B yet. Or, and you always have to look for this because you never know when it might rear its ugly head, you can recognize that it just so happens that all three of these positions are separated by the same angular difference of 120 degrees. So what we could do is, instead of saying everything that I've written in red on the left, if you recognize that these are all separated by 2 pi over 3, you could just say x equals multiples of 2 pi over 3. Because the first one is 0, so you just go 0 plus multiples of 2 pi over 3. And you have to be on the lookout for that, because sometimes questions on exams give you, Peppermint Patty said this, Charlie Brown said that, Linus said this. Are they all right? Are none of them right? And there are potentially at least 2 different ways you could write this. I would say it's limited to 2. I shouldn't have said at least. I don't think there's a third way for a general solution. All right, so now let's look at B. And please, please do not turn into an angry mob and get upset with me. But I'm going to show you how we could easily come up with the solutions to that equation or any of the equations that were on your exam yesterday that asked for exact values using your graphing calculator. Okay, and you're going to be happy that you now know this. But I've learned from experience that if I teach this, which is I'm supposed to teach it, as a way to solve equations first and then teach you algebraic, everybody just tunes out. They don't get any algebra skills, which are going to be crucial in this unit. So, solve the equation graphically. Listen, if I had the following function, 2 cos squared x minus cos x minus 1 equals y, okay? Forget about this equation at the top and look at the function I've written. And I said, find the x-intercepts. X-intercepts are where y equals 0. Which means the x-intercepts of this function will be the solutions to the equation that I get if I change y to 0. Well, that's the equation I'm asked to solve. So all we need to do is graph this function. Well, there's some subtleties, and look at the x-intercepts of this function. And they will be the solutions of the equation. And there is more to it than this. There is, okay? But to begin with, now, when you look at cos squared of x, what cos squared of x means is cos of x quantity squared. When you enter on your calculator cos, it forces a bracket on you, right? And you're going to go x and you're going to end this. You do not need to put that thing in its own set of brackets. If you do this on your calculator, it knows you're squaring cosine and not just x, which is what we want. If you wanted to just square x, then you would put the squared inside of the brackets there with the x. So, in other words, it doesn't quite look right. You might think I'm squaring x, but I'm squaring cosine. Minus cos x, just double check, was it minus cos x minus 1? Were they both minus? Okay. So here is the plan. We want exact values in radians, but I won't recognize radian angles. So I'm going to cheat the system and go in degrees. And I'm going to, for this question, since, how can I put it? Do you recognize that this equation is just like a math equation? It's like something from Unit A. It's got no context to it. It's got no application. Go zoom trig. Okay? So, now I didn't change my, I shouldn't say I didn't change anything. Those ticks are meaningless right now. I think the ticks are every 45 degrees. But if we find, for example, well, I hope it's obvious there's an x-intercept here, an x-intercept here, an x-intercept there. We're going to look from 0 to 2 pi, and then we're just going to add multiples of 2 pi. So this one is 0. Bad color. This one is 0. This one is at 2 pi. What are these two? Well, use your calculator functions, specifically second calc, 0. This is how we find x-intercepts. Put your cursor to the left of the x-intercept you're interested in and hit enter. Put your cursor to the right and hit enter. Oh, 120 degrees, 2 pi over 3. I'm not going to spend class time doing this process for each x-intercept. You're going to discover that this is 2 pi over 3. This is going to be 240 degrees, which is 4 pi over 3. And looking at the graph, I hope everybody knows or sees that this, which you don't need to know that's what it looks like by looking at the equation, that's going to repeat every 2 pi, so add 2 pi to those. Another thing you can do is the following. Go to your table set, start at 0, you need to be in degrees, and go up by 15. Always 15. The reason is 15-degree chunks will always hit all of those special angles on the unit circle. It's going to hit 30, it's going to hit 45, it's going to hit 60, it's going to hit 90. And now if I go to my table, I can just scroll down. Oh, there's one at 0. I'm looking for y equals 0. Oh, 120, 240. I don't know what we really need to write down here. You can solve it graphically on your calculator. Okay? Now, before we get to the last example, I really want you to focus on what I'm about to tell you. That this equation can be solved graphically because it's maybe easier to get an answer graphically. Okay? But it can also be solved algebraically. And you are expected to be able to solve it algebraically on a written response. Okay? However, if we take, well, I'll stop. Any questions with B? However, this equation, as far as we're concerned, cannot be solved algebraically. Okay? You never want to solve an equation like this algebraically. You only ever want to solve an equation, and by the way, we're solving for theta here. You only ever want to solve a trig equation if there's a coefficient of 1 in front of theta, algebraically. If there's any other coefficient, in other words, if there's a b value, you don't do it algebraically. So I'm telling you that for this, you must do it graphically. Now, follow along carefully, because we're going to continue to do this next class. I do not see a degree symbol. Okay? It isn't that I see pi that's telling me I'm working in radians. It's that I don't see a degree symbol. So your calculator needs to be in radians. Okay, done. Now, I do not like finding x-intercepts. So what your textbook might suggest you to do is subtract 10 from both sides and graph y equals the whole thing and look at the x-intercepts. I think that's a bad plan. What we're going to do is graph y1 equals the left side and y2 equals the right side. And somewhere along the way, whether it was in Math 20 or Math 10, or perhaps it cropped up in this course earlier this year, somewhere along the way you need to understand and have been taught that where two functions intersect, if they're equal to each other, are solutions to the equation that they're equal to each other in. You also need to appreciate before we proceed here that this is going to be our x in our calculator. So when we find where they intersect, we're interested in x coordinates. Now, the other thing is zoom trig is not going to work in these questions. If you go zoom trig with this question, it's just, you're not going to see anything. What you want to do is the following. You always want to have your window setting for x to be 1 period. You always have to set your window setting to show 1 period. Okay? Which means we're going to need to know the period of this, and we'll get to that. Vertically, you always want to go at least to the maximum value of the function and the minimum value of the function. Okay. And finding out what the maximum and the minimum are, and finding out what the period are from the second to last lesson in the previous unit. You look at this and you say, for y2 anyway, d is 8, a is 6. what that means, and I'm going to construct just a little tiny graph here. What that means is that up at 8 will be the middle of the graph, and it will go 6 above and 6 below. Right? This is 6, this is 6, and this is at y equals 8 because 8 is d. So if I take 6 away from 8, that gives me 2. If I add 6 to 8, it gives me 14. I would probably go from 0 to 16 for y. Okay? So again, this is equal to 2, this is equal to 14, but I like a little bit of cushion room. Okay? What's the period? Well, the period is 2 pi over b. Don't try to make sense of the colors I'm using. I'm just picking whatever pen I have. This is 2 pi over 4. And I think at some point I have to just say you should be able to see that that's 8. You would show that work on an exam by multiplying top and bottom by 4. So that means we should go from 0 to 8. Always go from 0 to the end of the period. And I wouldn't recommend, there might be the odd exception, I wouldn't recommend going before 0 and after 8. Okay? All right, let's do it. So I am entering for y1, 10, and I am entering for y2, 6 cosine. Now, I'm not going to enter pi over 4 times x. I'm going to enter pi x divided by 4. Okay? Let me just type down here what it would look like if I entered pi over 4 times x. These are the same thing. They're the exact same thing. But doesn't this look like I'm dividing by 4x? It does to me visually. I see divided by 4x. And that's why I don't like it. What else do we have? Then we have plus 7. I'm going to close the brackets, and we're going to add 8. And by the way, we're going to have answers in decimals here. In any of these ones where we have to do it on our graphing calculator, not algebraically, we're going to get decimal answers. And it's very useful not to worry about the fact that it's theta. It's just a variable. Don't think of it as an angle. You'll mix yourself up. Double check to make sure you've entered it all correctly, and we're fine. We are in radians. We've set up our window setting. Oh, no, I haven't done that yet. Window settings for x want to go from 0 to 8. For y, I said from 0 to 16 would cover it. If I've done things right, the sine function, or in this case cosine function, will be visible for a full period in my window screen. There's 10, and here is the sine function. And I want to point out to you that since this is one period, it keeps repeating. I'm looking at one of those cycles. It may not be starting in the middle and ending in the middle, or starting at the top and ending at the top, but it goes back to the same relative position that it started at. So what are the solutions? I can see that in one period, I just want to get rid of this stuff. In one period, there are only 2 solutions. So I need to find them. Calc, intersect, which is much easier to work with than zeros, which is why I prefer this method to the x-intercept method. Move close to one of them and hit enter 3 times. One of your solutions is about 0.65. We'll repeat the process for the other one. By the way, and I don't know that I've ever really said this, you don't have to scroll. Did I say I went from 0 to 8? Is that what I did for x? Okay, you can just enter the left boundary. I'm looking at that and saying, I'm looking at that and saying that 8 is here, so I would say 4 is to the left of that. So I can enter 4. Whoops. Does this work? Intersect. Left. Oh, it's first. This, forget about what I was going to tell you. It doesn't. It only works for zeros. I do have to scroll, I think. I don't think there's another way to get over there. No. You do have to scroll just so you're closer to the other curve. There's your other one. Are we okay with finding those? Okay. What are we asked here? We're asked to solve this graphically. So if it said in one period, then you would put these two numbers. But because it says solve it graphically, we want a general solution. And I would like you to understand that if this is 0.65, and this graph repeats every 8, this point will be 8 plus 0.65. This point will be adding another 8 to it. Capiche? So what we're going to say for the general solution here is that theta equals 0.65 plus 8n. It's not 2 pi n because the graph doesn't repeat every 2 pi. It's 8n because it repeats every pi. And then we can do the same for the other one. 5.53, 5.52 plus 8n. Are we okay with that? Any questions with that one? All right. Perfect timing here. We have one more to do. I'm not going to explain the details of this on paper, so to speak. I'm going to ask everybody to look at the left-hand side of this, which we're going to call y1. And I want everybody to do two things. I want you, first of all, to find for the left-hand side the max and the min values of y for that function. And for the left-hand side, I would like you to determine the period of that function. You're not looking at the 300. You're not looking at the negative 300. I hope that makes sense. D is a whopping negative 740, which means the middle of this graph, which happens to be a sine graph, is down at y equals negative 740. The amplitude is 520, so the maximum will be 520 above that, and the minimum will be 520 below that. These are going to be what I use to determine my window settings vertically. What do we get here? Negative 220? Negative 1160? 1260. Okay, thank you, Ellie. Negative 1260. So I have to go from, the x-axis is the ceiling, everybody. I have to go from negative 1260 up to negative 220 vertically. This is my y min on my graph, and it's my y min in my window settings. What is the period? I hope you got the period equals 2, because the period will be 2 pi over b, which is 2 pi over, in this case, pi. That's weird. B is pi. B doesn't have to be a number like 2 or 3 or 4. B is the number in front of the independent variable. And that gives us 2. What does that tell us? That tells us that our minimum x should be set to 0, and our maximum x should be set to 2. I would prefer to have a little bit of cushion here vertically. I don't want to start exactly at negative 1260 and end at exactly negative 220. I like cushion vertically so I can see above and below the peaks and valleys of the graph. But I don't want cushion room horizontally, because all I want to see is exactly one period. If I need more than one period, then I can expand my horizons. So now that I've got all of that established, don't worry about what I'm doing. I'm going to put 520 sine brackets pi x plus 12. What that 12 does, we don't care. We're solving an equation. Okay, we're done with analyzing that function. Close the brackets, and then minus 740. And then we also have negative 300. Of course, you should always double check everything before you go graph. My thinking there is, as soon as you go graph, you can no longer see what you've entered. So you don't get a chance to check it. 520 sine of pi x plus 12 minus 740 and negative 300. So if you look up here, you're going to see something which you should not see on your calculator. Okay? But it's going to happen to all of us sooner or later. Did I not enter? Oh, I didn't change my window settings, right. 0 to 2. And what did I say? Negative 11, negative 1240 or something?
It's negative 1260.
Okay. Oh, negative 1260, but I want some cushion room. I'm going to go negative 300, negative 1300 rather, to, I don't know, negative 150 in increments of 100. So I'm going to now graph it, and you're going to see something that you up here that you're not seeing on your own calculator, okay? It's that my sine function is a straight line. It doesn't have a curve to it. And everybody is going to do this at one point. You're going to do that and go, I don't understand what's happening. Or in this case, I guess my sine function doesn't really look like a curve. I don't know if you noticed, but I got out of radians and I changed it to degrees. If you've done things right and it doesn't look right, you're in the wrong mode. Okay. Oh, that's better. So there are 2 points of intersection there, which means there are 2 solutions in the period, in the first period. Would you please do me a favor? I'm going to let you do it this time and use your intersect function on your calculator to determine the x values of both of those. How many of you have them already? Okay, Brody, while other people are working on them, can you tell me what you got for the first one?
The first one was 0.501.
0.501. And the second?
0.859.
0.859. And I don't care whether it says to the nearest hundredth. I don't even know that it says. It doesn't matter. You would be directed that way on an exam. If you were asked, this will be important for next class, if you were asked, in the first cycle, what are the solutions? There they are. But as a general solution, we are going to say plus multiples of the period, right? That it's not always plus multiples of 2 pi anymore. It is if there's a 1 in front of your x, which means it repeats every 2 pi. Here, it's not that way. So what was the period? 2? Okay, so x equals 0.501 plus 2n, and x equals 0.859 plus 2n, n, of course, is an element of the integer number set. When we return after the break, we're going to be looking at applications. I talked about time of sunrise, talked about the depth of water in a harbor due to tides. Those are going to be problems that are modeled after these types of equations that you can't solve algebraically. So looking forward, it's very important you understand this process. I want to go back to this one. That everything that you can see on the screen right now is used merely to set up your window settings, right? You need to do that. You need to remember a 1 period and make sure I can see the minimum and the maximum. And to find the minimum and maximum, you look at A and D in the function that is sinusoidal. Sinusoidal means sine or cosine. And to determine the period, you use 2 pi over b equals the period. And unless you see a degree symbol, b in radians, I believe, I've assigned you a couple of problem sets at the bottom, right? 4 and 5 on page 275. There's nothing to do with the tangent function here in your assignment. You just need to know all the properties of tangent. Those are all equations, like equations in this final example. Okay. Can you look at those? Do any of them have a degree symbol on them? Some of them do, eh? So that's going to be really unusual when we get back from the break and start looking at applications. I've never seen a degree symbol on applications. But if you see a degree symbol, then you're going to do the exact same thing, except you're going to be in degree mode. And when you do your calculation for the period, you're going to have 2 pi, instead of 2 pi over b, you're going to have 360 degrees over b. That's it. I think you should be able to just do these pretty much all on your calculator. I don't really care if you write much down here. What I care about is that you know how to find the answers on your calculator. Okay? So I hope that you can probably get that done, or most of that done, before the end of the class and not have to worry about math over the break.